we saw that the worst case complexity for jump search is n by m plus m minus 1. Again, like I said, this tacitly assume that n is divisible by m. Doesn't matter. Let's go with this formula. N by m plus m minus 1, because the insights we are going to get from this are quite unique, quite nice. Let's say, take few situations. Let's say m is equal to 1. Now clearly, if m becomes equal to 1, well, we are back at linear search. So you can think about it. Linear search is actually a special case of jump search, right? So when I make m equals to 1, basically I'm looking at every item just like linear search, and indeed the worst case complexity then becomes n by m plus m minus 1 equals to n, exactly what we had seen with linear search, right? Because worst case scenario, I'll have to look at all the items just like linear search, right? So similarly, if I were to make m equals to n, now this requires a little bit more thought. Basically, once again, this number becomes equal to n, which means again we have a linear search. But why so? Let's understand this. But we can see this by looking at this diagram. If I made, let's say, n equals to m, so basically I'm going to go here. I'm going to go all the way to the n, and which means I'll have to come back to this point again, right? So and then do a linear search. So effectively, I again have a linear search. It doesn't really help me making such a large jump. This function n by m plus m minus 1, in fact, can be minimized. So you know that at the two extremes, it is basically n. It turns out that if I set m as square root of n, now this is very interesting. If n is set as square root of m, we get the number to be 2 times square root n minus 1. And using, let's say, arguments with this differentiation, we can prove that this is in fact the lowest value. So which means that, look, this is a significant result. Notice that if I were to, what this basically is saying is that, look, if I were to set the jump size as square root of n, basically my worst case complexity is the lowest possible, and it's a function of square root of n. Remember, for large values of n, square root of n in fact is much smaller compared to n. So what is this telling us? This is telling us that for large sorted lists, it's in fact much better to do a jump search with a step size of square root of n. And again, this aligns with intuition, because remember, the list is sorted. It really did not make sense to go every item as we do in linear search. It makes sense to jump. And what this is telling us is quantifying this even more. It's saying that, look, the jump should be made in steps of square root n, because that way you'll have the least, let's say, worst case complexity. In fact, we will quantify this later, but at this point of time, I would like you to make a small compare and contrast. We have a square root n increase in the worst case complexity. Remember, as n becomes large, square root n is much smaller than n. In fact, this is exactly the gain that we made as we moved from the naive prime value, let's say prime number searching, prime number determination algorithm, to a smarter algorithm that searched only until root n. And we saw it there. The difference in performance was startling. So once again, think through see the similarity between the prime number problem that we are looking at and this search problem. We'll come back to quantify this in a later experiment, but before that, let's look at binary search. I hope you find this interesting. Do look at our website www.ybyte.in, because we have a lot of content for you to learn programming from basics, algorithms, and let's say have fun doing it. Take care. Thank you so much. Bye bye.